Thank you. I do have two jobs. My main job, what I call the day job, is I'm Vice Chancellor at Irvine. I've been doing that job for 22 years now. I have this other job. I'm chair of the University of California Climate Solutions Steering Group. And that's actually where Kathy Haq comes into the picture, because she talked me into chairing that group about 7 years ago, I think it was. And she said it would take about 5% of my time. Kathy lied. Don't be careful. If she ever asks you to do anything that's going to take 5% of your time. That's a major part of what I do. Is I chair a group by steering group. It's not a committee, actually. Committees write reports. I hate to say it. In the University of California, the typical report written by a committee usually ends up recommending that another committee be formed to answer all the questions that committee couldn't really solve. And in this case, it's a steering group which actually works with the executive vice president of the UC system to develop and then implement a climate action plan to get, in our case, all the way to carbon neutral. I'll talk a little bit more about that in a minute. But first, let me tell you what we hope to do today here. I've come with a team of people. I'll introduce them later. We're going to tell you not only what we have done to make our laboratories more efficient, but why we did what we did. We're going to talk about our initial concerns and skepticisms, what we learned along the way, and where we are today. And I want to say right at the outset that some of us here, some of the members of my team, were skeptical about some of the things we have now done. I'm probably the biggest skeptic in the group. Katie used to say borderline cynic, because I'm very suspicious of claims of breakthroughs. What we were hearing a few years ago was about some technologies and some different approaches that sounded to me things I needed to be skeptical about, and we all shared this view. So that's where we started. And let me also say at the outset here, we're not here to sell anything. We realize that some people will look at the same data that we looked at, look at the same circumstances that we were trying to cope with, and come to different conclusions and actually design different solutions. And we're actually very interested in hearing about different approaches to laboratory energy efficiency, because for us it's really important. And here's why. We use a term called deep energy efficiency in our energy efficiency retrofit program. That's a term we coined to separate the projects that save less than 50% of associated energy from the ones that save in excess of 50%. And actually, the first time I heard that term, I was skeptical, because I thought the guy who said that was over the top. Then we started, and then I heard it from another person. Actually, I heard it from first the head of the California Institute for Energy Efficiency. A couple weeks later, I was at the California Lighting Technology Center, and I heard the director there, Michael Siminovich, use the same term. And I was pretty sure he was over the top. And now we have actually a list of projects that we have completed, and they're not all in laboratories. They're in three areas. They're in laboratories, they're in illumination, and they're in data centers. It takes now, in a different presentation, it takes 4 slides now just to list all the projects, not theoretical ones that would theoretically save more than half, but we've completed all those projects now. We know that they all save more than half. And so and the reason we're doing this is because in California, there are some things really leaning on us heavily to make progress. One is Assembly Bill 32, passed by the California Assembly. This is, you've probably read about the cap and trade system in California. That's, the foundation for that is the statute, AB 32. Practically every policy being enacted by the California Public Utilities Commission or the California Energy Commission is now derived from the environmental goals, the climate goals actually, set by AB 32. The University of California, as a system, all the campuses, all the chancellors together in 2007 signed up for the American College and University President's Climate Commitment. That is a commitment to become carbon neutral. At that time, the the stated goal to become carbon neutral was as soon as possible. And different campuses had different interpretations of what that meant. So if you looked at the climate action plan for Berkeley, it was different than, say, UCLA. And this was all clarified down to one goal, which has now been publicly announced, established under the leadership of our new president, Janet Napolitano. It's now 2025. We intend to become carbon neutral. And actually, that group I chair, the Climate Solutions Group, has developed a plan called Prospectus for a Sustainable Future. I won't spend much time today talking about it, except to say that deep energy efficiency is the most viable first step that we see to approach that goal. We're still at a point, even in California where the wind blows and the sun shines, we're still not finding that renewable energy quite pencils out. So with this group you see here today, they've spent 99% of their time over the past 5 years working on deep energy efficiency and 1% of their time working on trying to get more renewable energy on campus. That's actually been a good thing because the price of renewable energy has come down enough during this 5 years. We're just on the verge of probably within a month or two announcing another major solar installation on campus. It wouldn't have been feasible, though, up until now. So the way we count the fraction of energy and carbon footprint associated with laboratories gets us to about 2/3. And I've seen that across all the other campuses in the UC system. I see the data for everybody because of this system-wide role that Katie assigned me to. And the reason we say 2/3 and she said 1/2 might be because the way we look at it is since the campuses differ so much in terms of auxiliaries and particularly housing, we're looking at the core campus. So if you look at the academic core of the campus, it's 2/3 across all UC campuses. It's about 2/3 in all of the Midwestern universities I've looked at. It's typically 2/3 in the UK. The highest number I've heard is actually at Oxford, where it's 86%. 86% of their energy is laboratories. 14% is everything else. So it's on the critical path for us to achieve this goal. Now I know that facilities and environmental safety people understand why laboratories have such a high energy profile, but just for the sake of perhaps some administrators in here, if there are any other vice chancellors, for example, let me just give a real quick overview of this. All laboratory air is once-through air. It's 100% exhausted. I'm surprised at how many of my administrative colleagues, business officers, don't realize this basic fact. What I always tell them is, when you see those exhaust stacks on the top of a typical laboratory building, understand that every 6 to 8 minutes in a typical lab building in the United States, the entire volume of air in that building is being exhausted to the atmosphere, including all the thermal inputs, all the energy it took to pump it through the building, to heat it, to cool it, humidify it, dehumidify it, filter it, and then exhaust it, typically at pretty high air speeds out of those exhaust stacks. And this happens 24 hours a day, 365 days a year, typically in laboratories, in every space, regardless of whether there's anyone in them, and regardless of what the quality of the air is in that space. And this is what I'm calling typical. I realize may not be typical in all situations, or it may not be the case in all situations, but I think it's pretty widespread. Because it has so much to do about this massive flow of air and the thermal inputs associated and other energy inputs associated with air movement, what we do centers around that, but that's not all we do. We take a holistic approach, which we'll try to explain. So let me tell you how we got into this. Initially, we didn't foresee the concept that we now call smart labs. It started when actually Katie Lapp funded, in her role as executive vice president of the UC system, a number of pilot projects and experiments. We got funded at UC Irvine to do these with the quid pro quo that we would share all the results with all the other UC campuses, because we were all facing this challenge of this daunting goal of getting all the way to carbon neutrality, and we all knew that our laboratories were on the critical path, being the primary part of our energy profile and our carbon profile. So Katie sponsored a number of projects. This was one. This was one where it turns out, it's kind of interesting, in every other state except for California, you can use a fume hood face velocity less than 100 feet per minute. And so this is a test that Mark Gomez here ran and actually presented the results to Cal OSHA in a 6-hour hearing. This is to determine whether a high-performance, low-flow fume hood is as efficacious at a face velocity less than 100 feet per minute as it is 100 feet, which is the standard in California. This is just an example of half a dozen different pilot tests that we did that Katie funded. And so this was where we sort of started. This was against a backdrop of a bunch of things I'd been getting concerned about and skeptical about for decades, I guess. Well, the first thing, here, let me say this. I got a little bit out of order, but it turns out that UC Irvine was a campus that I think we were among the fastest growing research universities for about a decade. We were the fastest, that was about from 1995 to 2005. We actually built a new laboratory building every year for a decade. This was a real growth spurt in California, and we were able to deliver projects faster than other campuses because of the way we used a design-build process that kept producing projects quickly, on time, and on budget. So we kept getting funded, and we did a lot of lab buildings. We used the Labs 21 toolkit for all of our projects starting in about the early 90s. And this was a good toolkit. We made good use of it, but we started to get concerned that it was plateauing a little bit in terms of increased energy efficiency in about 2007 or 8. I'd been going to value engineering sessions during this entire period of time. I'm a little bit unusual, I guess, for an administrative vice chancellor. I actually go to the value engineering sessions for new capital projects. And the reason is, these are huge capital investments. I feel I'm accountable to in our case, the taxpayers of California to get high value and to make sure these projects get done on time and on budget. And so I want to know the kinds of decisions that are being made very early on in design of these projects. And we do value engineering very early because we think that the best impact from value engineering isn't after the project is designed, but actually at the programming stage, at the end of completion of programming. And these are statements I actually heard for years. And I started to get worried about some of these statements. I heard mechanical engineers say many times, energy is almost free. Design with a margin of safety, a certain amount of reheat is inevitable. I remember the first time I heard about reheat, I said, why is that necessary? And well, it's just inevitable. This is the way it's designed. It's considered best practice. And so I got more and more concerned the more I heard about this. I really started to get concerned about whether this phrase margin of safety was really about safety. I got skeptical because it seemed to me that it was about avoiding complaints and litigation aimed at all the actors in the picture of designing buildings. That includes the MEP designers, the executive architects, and even the laboratory programmers. So that's kind of where we got started thinking about whether the status quo was as good as people claimed and whether it was really best practice or not. Probing a little deeper, I started to get concerned because for every one of these new laboratories, I was aware that they went through a pretty exhaustive wind tunnel study to determine what the parameters should be of the exhaust system, and particularly the discharge airspeed coming out of the exhaust stacks. And what made me really skeptical was, I knew we were paying a lot of money for these tests. They always came back with the same answer. Well, if you're a CFO, I'm not an engineer, I'm a CFO. If you pay a lot of money, you keep getting the same answer, you start wondering what's wrong with this picture. And I did understand that the wind tunnel tests are done at an early stage when the building is not fully designed, and so there have to be some conservative assumptions put into a study like that. But what I didn't see happening was then as the building finally got refined into its final design, it wasn't really, some of these assumptions were left unquestioned as they went through to closure. So, and then there was one other thing. We started actually at Irvine back in 1991. When I came there, I established a policy that we'd beat code, California's code. It's called Title 24. It's pretty similar, I think, to, is it ASHRAE 90.1? So we set the goal to beat it by 30%. And this was before I'd ever heard of the Green Building Council. We had never heard of the ACU-PCC. This was because we had a budget deficit. The reason was we were building a lot of laboratories at Irvine, and the odd thing about the way California is funding utilities is you got the same amount if you build a humanities building or a laboratory building per square foot. You know what, you know where that leads to deficits. So we just started this goal of having our design build teams show that they could beat Title 24 by 30%. And it occurred to us they were doing that all the time. And so we thought, well, how much further could they go if we really wanted to throw the book at all possible new ideas at a new project? So, so we were in this position where we were questioning the status quo. We had this audacious goal of getting all the way to carbon neutrality, and then we got a big opportunity. And we had all these pilot tests, and the pilot tests, for the most part, were turning out to be pretty positive in terms of their outcomes. So, before I go on though, let me say something about safety. This is really an important point that we established as a principle on our campus early on, and I'll tell you why. This is a chart that shows all of the workers' compensation rates for all the other campuses. Now, I didn't label them. I just called them B through whatever that is over there, J. So these are actual numbers from other campuses. One of these is Berkeley, one's UCLA, one's UC Santa Barbara, and so on. This is UC Irvine. What this vertical axis is this is dollars per $100 of payroll that we pay into a workers' compensation fund. So this is based on an accrual rate that is a very accurate surrogate of illnesses and injuries that result in payouts for workers' compensation. So this is a very good surrogate measure of safety. We're half of the UC system, half. That's actually much due to the good efforts of Mark Gomez. Mark Gomez, before I promoted him to be head of facilities and environmental safety, was head of environmental safety, and this point here used to be up about here. We were always better than the system, but it dropped about half under Mark's leadership. We're not going to compromise on this. This is really important to us, and it's really important not just because this represents across our campus a lot of dollars, but the main thing is this difference here represents a lot fewer cases of human misery, fewer illnesses and injuries. My boss is an MD. He firmly believes that this is the most important reason to make safety paramount. And we all agree. Everybody in my team, everybody who works for Mark is firmly committed to this goal. And I want to say that because it's always a question that people wonder about. There will be no compromises on our campus it doesn't matter how much energy efficiency may be gained. If it compromises safety for students, faculty, or staff, we will not do it. So we had an opportunity that occurred. There was a big bond issue in California. You may have read about it. There was a lot of litigation. It was to support stem cell research and some stem cell institutes. The litigation was from groups that opposed stem cell research, and it slowed down the construction of these new buildings quite a bit. But anyway, we had a building that was funded through this bond issue, and so we decided to basically throw the book at it. We said all the pilots that we'd been doing, we wanted the design build team to try. And the goal that we gave them was to beat Title 24 by 50%. We didn't know if it was possible when we set that goal. It turned out that it was, with 0.4% to spare. This building is a LEED Platinum building. It certainly was, when it was completed, the most energy efficient wet lab building ever built in California. We think it probably still is. There are other smaller buildings that have been platinum and claim to save 50%, but this is a real wet lab building. This is a health sciences research building. And so this was our first experience with smart labs. And what this did was actually raise a number of interesting skeptical reactions. And I understand skepticism. I would have been one of the people asking these questions. The first question we heard was, well, maybe you can do this with a new building, but can you do it with retrofits? Another question was, can you replicate this result? Maybe you got lucky once. A third thing we heard was, this was a real serious concern, actually, that I heard internally from our own people. Can we afford to keep a smart lab smart? And if we can't, if it goes out of whack, will we be worse off than if we'd never done that in the first place? And then a lot of people, especially in the Midwest, were saying, maybe you can make this work and actually pay off in California, but would it be cost beneficial in a state that has, let's say, electricity at 6 cents per kilowatt hour? So we, frankly, shared some of these same concerns ourselves. And before we launched the program that we now have, where we're doing every building on campus with what we're calling the Smart Labs approach, we did one pilot. In our workshop today, my colleagues will provide data that focus on these questions that I just raised. And there are also a couple others here that I heard in value engineering sessions over the years. One is a lot of programmers, laboratory programmers, said we needed to be prepared to remove the heat from power densities as high as 10, or maybe even more than 10 watts per square foot. We'll see some, I think Matt's going to show us some data on that. And then I also found there was this, what I call a conspiracy between mechanical engineers and architects who never even talked about this, but the mechanical engineers assumed that the architects wouldn't tolerate having the exhaust stacks extend above the height of the parapet. So we actually had a number of buildings that were built that way. And that has a major impact on exhaust fan energy, and Fred will talk about that later. Now let me give a quick overview of the financial aspects of this, because some people wonder, how are we paying for this? A large financial investment is required to do this kind of program. The capital costs are not trivial. The payback is typically 5 to 8 years for these smart lab retrofits that we're doing. However, the savings are very high. The Irvine campus, for example, has invested right now $50 million in 15 laboratory building retrofits. Don't divide 50 by 15 to think you got an average number, because the ones that didn't start out with being variable air volume cost more. We did that conversion first. We converted constant volume to variable volume. We did different things. We had a dual duct system building as well. Those things cost more than if you start out with a VAV building with direct digital controls. We think that it makes sense to do a pilot first. And we don't think it makes sense for a campus who's only got one lab to do one smart lab, because what we're going to describe today to you is not a project, it is a program. We changed everything about the way we view the function of a laboratory as a machine to deliver safe environmental conditions for laboratory work. So it's a program. It applies to a number of laboratories. And by the way, now speaking as a CFO, I have to tell you, we consider this now a low-risk investment. I didn't consider it a low-risk investment when we started out 5 years or so ago. But what I mean by low risk is projects are not costing more than projected, and they're not delivering less energy than projected either. So that ratio is very important. Mark Gomez and I are on the hook to make sure that the savings are adequate and sustained enough that we meet debt service obligations. And they do. And in fact, there's a significant margin in excess of the debt coverage requirement. Now, your mileage may vary for these reasons. Most of these actually, I think for institutions here, actually work to your advantage. I go on sometime I won't do it today, but at length I'll talk about the fact that the time-weighted marginal cost of energy is what you need to be looking at. It's the time-weighted value of the megawatt hour you don't have to buy from a big project like this. And that's different than your average cost of energy. You'd be surprised how many CFOs don't understand the difference. And a lot of facilities people get into discussions that don't go anyplace with their CFOs when they start talking about this. It's a topic all its own. We do have a pretty generous rebate program in California. It's providing about a 20% rebate on these projects. That was an incentive for us to go deep, I would say, and that was a big plus for us. Our climate is, let me tell you how many degree days we have. You'll be surprised at how different it is. Irvine has 1,100 degree days of cooling and 1,600 degree days of heating per year on average. So when I talk about this in the Midwest, for example, they may be paying 6 cents per kilowatt hour, but the number of degree days that they have in Madison, Wisconsin is phenomenal compared to us. So they're actually going to come out ahead even with lower cost of energy. So that's how, and the prior lab parameters, that's mainly about what the air changes were before you started. And it's higher than people realize in a lot of cases. We found it was higher than our buildings had been designed for because different people have been adding in these margins of safety. And it turns out that the margins of safety, it started with programmers, it went to MEP designers, it went through executive architects. Everybody was adding a margin of safety. It really added up. Now, the way this was financed as a whole for us is Katie Lapp actually was the leader in California who took to the regents a proposal which they financed. We fund it with revenue bonds, the same kind of bonds we use to build student centers or dormitories and so on. They're not 30-year revenue bonds as they would be for those things. They're 15-year revenue bonds. They are tax-exempt bonds, so there's a low cost of capital. They have one major criterion in them, and that is that the debt coverage ratio must be 1.15 or better. That means that in year one, the actual savings has to be 15% better than the debt service obligation. And for us in California, because our energy costs are going up at real rates of inflation, that is, real cost increases, meaning that the cost escalation is a couple percentage points per year greater than the background inflation, that is, i.e. price inflation. That means that by year three, we're already up like at 1.5 debt coverage ratios. In 10 years, we'll be at 2.0 or more. It just gets better, actually. And there are some other financial and non-financial benefits. I'll just quickly run through them. We actually have had enough savings through energy that we've channeled some of that money back into improved laboratory safety. And I think Mark or David will talk a little bit about that. We discovered many mechanical components we didn't know were broken in the process of doing these projects. We in essence, funded a huge deferred maintenance backlog, including some things we didn't even know we had in our laboratories using energy savings. So that's a big plus. We actually have photographs. I don't know if you brought some of them, but we have photographs where we have done thermal imaging of the bearings of motors, and so everything every moving part that has been slowed down, motors, fans, and pumps, those are going to operate way more than twice as long as they would have. So we've extended the life of all these things. Matt will talk about how the real-time data that we get through what we call the information layer actually provides us with we believe, real-time commissioning information that will prevent us from ever having to spend money to do a complete recommissioning every 6 or 7 or 8 years, as we're supposed to do. We don't think that's necessary anymore. And then the final benefit is a concept that Mark Gomez is responsible for, which was to take all the data in this information layer and take it out of the back room, where, at least in the University of California, it's been for decades. We didn't want people to know what was going on in the mechanical room. What was in facilities domain was not considered public. Well, we now put that data right in front of users, and we want them to be more aware of their environment. We think that's part of this new paradigm of safety. And so you'll hear more about that. And again, as I start out by saying, this is my closing point here, look at the data. We're going to tell you what we went through in terms of our thought process. I've told you already that we started out skeptical, but as we got more experience, we decided that we wanted to keep moving forward. You may come to different conclusions, and you may decide to do something different. And if you do, we want to know what that is, because we need to get to carbon neutrality, and we're going to need all the help we can get. So that is close my remarks, and I guess we'll take questions later in the session, because we're on a pretty tight schedule here. And I will be doing a breakout session this afternoon. I think it's on leadership and getting the administration to come along and that kind of thing. Thank you.